is the usual. Tomorrow, 1 o'clock, Bishop, main auditorium. We're going to do those tutorials, which is basically me working through homework. It will be recorded, posted on YouTube, posted on Google Drive, all that fun stuff. Yes. Oh, top hat. Hold on. This thing was slow. There we go. All right. Get rid of that. Go into this. Create. Create attendance. Eight 146. All right. Blah 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 blah. All right. Now, what we're going to do today is we're talking about fluids. Now, fluids can be, it could be air, it could be water, it could be liquid, gas. Over the past couple of weeks, we have learned about position and its units and how it could work to area and volume. And we have other things called like mass and time. And from position, we can get things called velocities and acceleration. When you mix position and time together, you can get velocity and position. And then we have things, if you take mass and acceleration together, you get force. So a lot of this stuff is we're mixing things together. And this is kind of a crude flow chart on how everything is tied together. With mass and acceleration, we get force. With force and position or distance, we get work or energy. And we all know the units that this stuff comes from. And so this is, now granted, it looks horrible, but you could sit there and think about it yourself and how the words all tie together, how the units tie together. I mix position and time, I get velocity. I mix time and velocity, I get acceleration. You do mass and acceleration, you get force. Force and position, you get work or energy. And so the stuff mixes together, it's all related. And one of the things that we've introduced in the Tuesday lecture is the idea of density. That's a horrible lie. And there is volume, density, surface, density, and linear density. Volume density is the one we're most familiar with. Mass divided by volume. Surface density is mass divided by area. Linear density is mass divided by length. And we've learned that the symbols for these things are rho, sigma, and lambda. Lambda is occasionally used as rho sub L, but I'm trying to try not to use this. So more often than not, I'll try to use lambda, sigma, and rho. And rho is simply mass divided by volume. And the traditional units for these are kilograms per cubic meter. When you're dealing with large quantities of anything, you're going to typically use kilograms or cubic meters. In physics, we use kilograms and cubic meters. In chemistry, some of you may use grams per cubic centimeter or grams per milliliter, but what we're going to try to use on a more regular basis is the kilograms per cubic meter. Some example densities: the density of water. Probably the universal density that we need to kind of remember is 1,000 kilograms per cubic meter. Or you could say 1 gram per cubic centimeter, or 1 gram per cubic milliliter. Another example would be density of wood. It could be, depending on the wood, like 500 to 800, even more kilograms per cubic meter. And these densities are just dependent upon the type of material. Now, in this course, you don't have to memorize all of these densities. Oh my goodness. This isn't botany class, this is not BISC, this is not biology or chemistry, this is physics. We don't memorize stuff. We understand ideas. All of these densities, if you need it, either A, I'm asking for it, or B, it will be put on the test. So don't spend any time trying to memorize stuff. I want to introduce, I guess, I'm the great discoverer of an element, and that element is called rebellium. Now, rebellium is a fictitious element purely created because I'm too lazy to memorize all sorts of elements and their densities. Rebellium, is it a liquid, gas, or solid at room temperature? Answer, yes. Is it lighter than air, denser than water, lighter than water? Yes. Rebellium is whatever I want it to be. So I was very amused by one student one year who said that the TA told him to just look it up on Wikipedia. It's in there. And I'm like, no, it doesn't exist. It's an element purely of my creation because sometimes I just need numbers. As an example, let's say we had a sample of rebellium that was 1 cubic meter. And it had a mass of 500 kilograms. The density of this rebellium is mass divided by volume, 0.1 divided by, oh wait, no, doing that wrong. 500 divided by 0.1, or 5,000 kilograms per cubic meter. Just as a kind of an example, like aluminum, 1,300 to 1,600 kilograms per cubic meter. Iron is about 1,700. Mercury is like 18,000 kilograms per cubic meter. So once you start working with these materials, you start getting a feel for these numbers and their values. One thing to note, I call this the Swiss Army knife equation. Because in many of the problems that you're assigned, quite frequently it comes down to, well, I got density, mass, or volume, and I need to get rid of it. What do I need to manipulate in order to get rid of it? Just throw density at it. And stuff like this, you can substitute either density, volume, or mass out of the equation by merely substituting a form of one of these three. So in many cases, if you're sitting there in a fluid problem and thinking, what am I supposed to do with this? Take that density definition and try to see if you can wedge it in. Trying to see what, is that all I need? Okay. So that's the introduction to density, and we need it because we're going to have to deal with the density of fluids, solids, all sorts of stuff. And if we take force and mix it with area, we get pressure. In fact, pressure is force over area. And one of the things that sometimes you just need to lie out. I mean, now I'm going to get into the physics and just talking about the beauty for just a moment, but just work with me here. If you were on a space station, what would you do? Well, the first thing you'd do is go, dude, I'm on a space station, just look out the window and just admire it. But let's say you mess things up and you open the window, what would happen? All the air would just get sucked out. Why? Because it's in space. If you walk outside and you just look up, there's no window, there's no wall, it's just air, and then what's above the air? Space. So why doesn't it all just get sucked away? Gravity. Gravity is, think of the air as just billions and trillions of little particles being held together by the mass of the planet, just pulling that stuff back. And what's really happening is that the Earth is pulling the mass towards its center, which to us means it's pulling that mass down right on us. It's stacked up on us. And another example that I used this morning is when I was 18, my mom taught a kindergarten class. I went to visit. So what do a bunch of kindergartners do during recess with an 18-year-old who's the son of the teacher? They all gang up on me. Now granted, I can take one or two kindergartners out, just lay them out. But when you got 25 of them and they all start stacking up on top of you, things get difficult. Now, when you're at the bottom of the pile, you're feeling that force that's stacked up above you. Much like right now, we're feeling the force of all that air stacked up in the atmosphere. Now to us, we don't really feel anything extra because A, we're used to it, and B, it's not really all that much. But on us, there's this huge column of air that's on top of us. And so this air has mass and also it has an area for the base, and so it's a lot like a big cylinder, like a big column of air. Now with this idea of all this air stacked up above you, we've got the idea of pressure, and so we need to kind of introduce a couple of topics. If we held A constant, if A is constant and P goes up, if pressure goes up, that's because force goes up, which means pressure is directly proportional with force. If we rearrange this, we can also see that AP is equal to F, and that if P is constant, and we increase A, then force will increase. So A is directly proportional with F. Directly proportional means if you increase one, the other one will increase with it, then that's directly proportional. In the case of pressure and area, if F is constant, if area goes up, then pressure decreases. So A is indirectly proportional with P. So we have that. So let's talk about pressure briefly in terms of hurting my student. Open-toed sandals, excellent. So let's just say I took my foot and stomped right down on her foot. That would hurt. Now, how could I hurt her foot more? Putting all my weight on, or increasing the force. So if I increase the force, that would hurt more. So increase force, increase pressure. So now for the quiet, oh, here's another pair of sandals, excellent. So let's say I wanted to use the same amount of force as this, just stomp down. But let's say I was required to keep force constant. How could I increase the pressure on her foot with the same amount of force? Decrease the area. So what I'd have to do is get my spike out. No, I don't have a spike. But if I had like a railroad spike and I put it right on top of her foot and then I stomp down on it, that would hurt even more because the area is decreased. So with that, that increases pressure. So to increase pressure, you do one of two things. Decrease area or increase force. And so that is kind of an illustration of the differences between directly and indirectly proportional with force and area. All right. Now, with all this stuff, pressure is force divided by area. And, well, what are the units of force? Well, force is Newton. Well, what are the units of area? Meters squared. So newtons per meter squared are the units of force. Now you can write this out and do all sorts of interesting things with it. A newton is a kilogram meter per second squared. So this can also be rewritten as kilogram over meter second squared. This is an uncommon way of describing it. This is quite common. And just like we have the Newton, and Newton is a kilogram meter per second. It's a shortcut way of taking a group of units and squeezing it down into a common one-fits-all type of unit. Pressure has its common units as well. 1 Newton per meter squared is equal to 1 Pascal. I think there's an E. So 1 Newton per meter squared is 1 Pascal. They're interchangeable, just like you could say kilogram meter per second is a Newton. There's another unit that we have, 1 atmosphere. And 1 atmosphere is 1.013 times 10 to the 5th newtons per meter squared, or pascals. Now, do I expect you to memorize what 1 atmosphere is in pascals? No. Why do I know it? I never memorized it. It just seeped into my brain because when you say it 5,000 billion times, eventually the neurons just go, I get it. It's 1.013 times 10 to the 5th. Done. Leave me alone. I got stuff to do. So eventually, with enough repetition, it just naturally comes in. I had no intent on memorizing that. It just did what it did. Let's do this. We have 3 cubic meters of water in a massless cylinder. It's 2 meters high. What is pressure caused only by the steel? And what is total pressure? Now, before we, and this is the pressure on the floor. So before we really pursue this, there is something that I do expect you to memorize if you haven't done it by now. And that is, I call it the Helmholtz rule. Helmholtz is the last name of my doctor, and one particular summer, I was still not giving the basic units of. Now, I don't expect you to know what the volume is. The volume is of a dodecahedron or a pyramid or some weird stuff like that. But sphere, cube, cylinder, I do expect you to know the volume and surface area of these things. And why is that? It's because you're a human being, and human beings should have basic knowledge of geometric shapes. And one particular summer, I'm going on that rant, and the students were like, "But we're not as good as your other students. Just give us the equations." And I'm like, "Fine, but let me tell you what I'm going to do. I'm going to go to my doctor, and I'm going to ask her for the volume of a cylinder. And if she answers correctly, no future class of mine ever will I write those values down in the equation sheet." So I went to the doctor. It's the end of the checkup. She goes, "Do you have any last questions?" And I was like, "Are you sure I can ask anything?" And she's like, "Yeah, I'm your doctor." And I said, "Fine, what's the volume of a cylinder?" And she goes, "Pi r squared h." Now granted, she did say it in the form of a question, and I don't allow that in this room, but she did get it right. So congratulations. If you ever want to thank someone for not having equations on your sheet, thank her, because she's responsible. She has not been in med school for 25 years, and she still knew what a volume of a cylinder is. So I expect you to. So that's it. Now, for this stuff, the volume of a cylinder is pi r squared h. I gave you only the height. So, and you can change that to area times height. And if you have 3 cubic meters of water, You also know that density is mass over volume. That means that the mass that you have is density times volume, which means it's 1,000 times 3, or 3,000 kilograms. The other thing that we could look at is I need to know what area of the plate is. So V divided by H is area, which is 3 divided by 2, or 1.5 square meters. So we get a lot of basic information out of this stuff. Now this object is pulled down by gravity with a force of mg, just the usual force of gravity that we've had before. Pressure is force divided by area. Now the force is mg, and we have the area. So mg is 3,000 times 10 divided by area, which is 1.5, and 30,000 divided by 1.5 is 20,000 newtons per square meter. And that's the pressure of the cylinder on the floor, caused only by, I'm sorry, it's not steel, it's water. I flash back to, in the current problem set that you have, we use steel. Now, the thing that I need you guys to understand is pressure is force divided by area. The force is mg divided by area. Well, mass is density times volume divided by area. What's volume? Volume is base times height. Rho h a g over a, which leaves you with rho g h. So this pressure, 1,000 times 10 times 2, 20,000 newtons per square meter. So we get the same thing. Now, one of the things, and this is probably a critical statement, is pressure is only dependent on height. We did figure it out using area and the total mass and blah, blah, blah. But at its core, area cancels out. The initial way was just the plug and chug way. The second way was the algebraic way. In the algebraic way, pressure is base independent. It doesn't care about, is the base a circle, a square, a rectangle? It doesn't matter. If you had a cone of fluid that was 1 meter high and you had a cylinder of fluid that was also 1 meter high, those pressures are equal. Oh, that's okay. All right, good. So it doesn't matter about the geometric arrangement. All that matters is the depth. The depth is the critical part. Now, the one thing that we haven't answered yet is total pressure. In this cylinder, the total pressure is the pressure caused by the the water plus the pressure from the air. Because if we had, I mean, granted, if it was just in a vacuum, that object would sit there and the only pressure on the floor would be the pressure of the water. But if it's outside or in this room, the pressure on the bottom is the pressure of the water in the cylinder and then the pressure of the air above it pushing down. Much like when I was buried under a pile of kindergartners, the total pressure on me was the first kid on top and then all the kids above them pushing down as well. And it's amazing. Kindergartners are only, what, 30, 40 pounds each? But if you get 20 of them, then you're talking about 2 offensive linemen of kid. And they got me. So total pressure, you just have to add it. Now, the easy way is all you do is you take that 20,000 newtons per meter squared and you add 1 atmosphere. Well, that's not going to give you an accurate answer because you can't add newtons per meter squared and atmospheres together. What you have to do is a conversion. What you have to do is you have to ask, like, if you've got this, a very relevant question to ask is, what units do you want this answer in? And if I didn't specifically mention it, then it's my obligation to give you the units. And let's say I said, I want atmospheres. Give me the answer in atmospheres. So then you would take that 20,000, divide it by 1.013 times 10 to the 5th, add 1, and that gives you not that. 1.20 atmospheres. So the total pressure at the bottom is 1.2 atmospheres. And that's the total pressure. Another way that we can talk about this in terms of total pressure are tire pressure. The total pressure in a tire is gauge pressure plus 1 atmosphere, or pressure, atmospheric pressure. When you have a tire gauge and you put it on the tire and psst, you hear that psst sound, that's registering the pressure above atmospheric pressure in that tire. So if the tire gauge, you put the thing on and it goes psst, and it reads 0.5 atmospheres, then you know that you're actually reading 1.5 atmospheres in the tire. So that is another example. Another thing that we can talk about is let's tackle total pressure again. You are, and this is one of the, I love talking about fluids because then I can bring in the whole idea of me scuba diving. When I was in high school and college, I was fortunate enough for my parents to get, my dad was transferred to a Coast Guard base on Guam, and for 2 glorious summers and Christmas breaks, I would go out to Guam and we would scuba dive every day. And so there's a lot of stuff that you can get from scuba diving and just the whole idea of physics. And one of the things is, the rule of thumb is for every 10 meters of depth, that's a horrible writing, all right, depth, you experience an additional 1 atmosphere of pressure. So at 10, 20, 30 meters is about as deep as you can get without needing special equipment or decompression. The pressure caused by the water is 1, 2, 3 atmospheres. But the total pressure, remember that when you're at the surface, you're experiencing just normal atmospheric pressure. So the total is 2, 3, 4. And at the surface, there is 0. Let's see, let's write a full table. Depth in meters. At 0 meters depth, there is 0 atmospheres of pressure due to the water, but the total is 1. So when you're down 10 meters, the pressure that you're experiencing is twice that at the surface. So remember, total pressure, gauge pressure, all that stuff. A lot of good multiple choice problems. So now that we've kind of introduced the idea of pressure and depth and all that stuff, we got to introduce the idea of Pascal's principle. And that is, if 2 points are level and in the same system, they experience the same pressure. And one of the things that we could talk about is, like, if we have a great big tub of water or fluid, and I wanted to compare that point and that point, and you would ask, well, what's their depth? And I would say, well, both of them are a meter underwater. And I said, well, what's the pressure difference between the 2 points? Well, they're at the same level. If the pressure over here was greater than the pressure over there, the fluid would move and the pressure would equalize. So at the same depth, those pressures are equal. Well, what if we make it a little bit more of a complex geometry and we cut out most of the basin, and so we have the fluid over there and the fluid over there, and I said, well, what about the pressures now? And you would say, well, what's their depth? And I would say, well, those depths are still 1 meter. Well, answer, P1 is equal to P2. As long as the depths are the same, it doesn't matter that I just cut out all this stuff. Pressure's the same. Well, what about at the top? Well, the pressure's still the same. They both are at 1 atmosphere. And one of the things that we can do to take advantage of this principle, is we can talk about hydraulic lifts. With hydraulic lifts, you go and get your oil changed. What do? They roll the car onto a support structure, they hit a button, and then the thing just lifts up. Well, how does this happen? We have our car and the car is on a platform that is an area of 10 square meters, and the car mass is 2,000 kilograms. So it is resting on a big platform, and that platform is right over this tube, more like a big pipe. And that pipe is filled with incompressible hydraulic fluid that doesn't, it won't expand or contract based on force. And over here is a little platform, and that area is 1/10 of a square meter. Now what's interesting is if nothing was over here and you got this big car over here, that car would just sink into the pipe, fluid would go spraying everywhere, and it would be a big mess. But what they do is they apply a force, and let's say there was a mass sitting on top of a plate. How big of a mass would be necessary to balance the car? So if there was less mass, this would rise and that would sink. But if there was greater mass over here, that one would rise. Pascal's principle, P1 is equal to P2. P1 is just the mass, or actually, let me do it right. Force 1 over area 1 divided by force 2 over area 2. That the force over the area for part 1 is equal to force 2 over area 2 of part 2. Why? Because they're on the same level. They have equal pressure. What is the definition of pressure? Force divided by area. Force is mass times gravity. So you get this, and gravity's canceled. So that mass on the left is A1 over A2 M2, or 0.1 divided by 10 times 2,000, and that gives you 20 kilograms. So 20 kilograms on the left could balance a 2,000 kilogram car. And so that's how we can take advantage of hydraulic pressure, or Pascal's principle, where a little bit of force on one side can produce a big force on the other. What's another way to take advantage of this? You may have heard something in your car called a master cylinder. And what a master cylinder is, it's a system where there's a whole bunch of hydraulic stuff, and one end is hooked up to the brake pad. And we just got done talking about brake pads with the Friction Lab. But on the other end, you have, this is the pedal, the brake pedal. And what you do is you push down on this piston that's on the other side of the pedal. This piston has a small area. The brake pad is a larger area. And what did we learn? We learned that a small force on a small area can create a large force on a large area. So this is why your force on the brake pedal can produce the force that stops the car. A small force on that pedal causes the brake pads to clamp down on the rotor with a much larger force, and so the brakes can actually cause the car to stop. So with all this stuff, there are many things in our world where we look at it and it's physics. One of the things that I'm sure you've done, you've had that annoying brother or sister, or you decided to just go for the top and go after your mom or dad, and you had a hose with water coming out. but your mom, dad, brother, sister, whatever, is just a little bit further away. They're just out of range. So what do you do to the hose to increase the range? You put your thumb over it. You decrease the area of this hose. And what I am illustrating is the equation of continuity. Equation of continuity is this: that the area times the velocity at one point must be the area times velocity for the other. If we had a pipe that had a particular velocity and a particular area, it will give the same product as the velocity times the area on the other end. If you had a velocity of 2 meters per second and you cover half the hole, A2 is equal to A1 divided by 2. So using the equation of continuity, A1 V1 is A1 over 2 V2. So V2 is 2 times V1, which is 2 times 2, or 4 meters per second. So there is an increase in velocity with a decrease in area. Now, one of the things that I tend to call the equation of continuity is conservation of flow. And what does this mean? It means that if 2 gallons per second are going into a pipe, you gotta have 2 gallons per second coming out. That if it doesn't add up, then fluid is disappearing somewhere along the line, and then things are broken. So if you've got a certain amount of flow going in, you gotta have that flow coming out. And when you look at A and V, A is in meters squared, V is in meters per second, or cubic meters per second, and that brings up that the volume can equal flow times time. The flow is this: the cubic meters per second. The time is in seconds. They cancel and you're left with cubic meters. So if you knew that like 5 gallons per second was going through a pipe, multiply it by 5 seconds, you have a total of 25 gallons that have passed through. Now, for the last thing that I really want to cover is I have a favorite equation. I have a second favorite equation. What's my least favorite equation? Well, my least favorite equation is Bernoulli's equation. I mean, just writing Bernoulli takes a while. Bernoulli's equation sets up the problem of if you've got a pipe and it goes up a particular height or comes down a particular height, and you have an area and velocity of the water going in, and you've got a velocity of water coming out of a particular pipe with area 2. If the pressure is a particular pressure at the bottom, what is the pressure at the top? Typically the velocity is an unknown, and you need to know the height difference. So let's say that area 2 was 0.2 square meters and that area 1 was 0.25 square meters. The velocity at the bottom was 5 meters per second. What else do I need? I need pressure 1 is equal to 10 atmospheres of pressure, just because I mean, just pick 10. In this problem, we're looking for the final velocity and the pressure. Now, some of the questions is, well, what's the fluid in the pipe? I'm going to say it's water. So that's 1,000 kilograms per cubic meter. And the last question is, well, what units do you want the pressure to be in? And I'll say, give P in newtons per square meter. So I want that final pressure in newtons per square meter. Well, let's talk about the equation that we're going to use. Bernoulli's equation is this: P1 plus rho g H1 plus 1/2, I know it's long, V1 squared equals P2 plus rho g H2 plus 1/2. See, I'm writing across the whole page and it's still long. V2 squared. So really it's the same thing, but all the subscripts are changed. What this is it's talking about pressure and the contributions to pressure by height or depth, and also by the velocity of the fluid itself. One of the things when you see a problem like this, you always go with the lowest point having a height of 0. So height 1 is 0, so that goes away. So yay, there are some things that I enjoy plugging 0 in. Now I'm looking for, well, really what I gotta do first is not even use Bernoulli's equation. With Bernoulli's equation, it's the second part. With stuff like this, you've got to use the equation of continuity, that A1 V1 is equal to A2 V2. So V2 is equal to A1 V1 over A2, 8 minutes. A1 is 0.25. A2 is 0.2, V1 is 5, so this is 25 divided by 4, I think, 6.25 meters per second for the final velocity. And now that we have the final velocity, we can solve for P2. P1 plus 1/2 rho V1 squared minus rho g H2 minus 1/2 rho V2 squared is equal to P2. So I'm just getting P2 over to one side. Now, the biggest thing, if you get a problem like that, it's a plug and chugger's dream. You just throw numbers in and you're going to town. The one thing that you need to pay attention to is the velociraptor pit that's trap that's within this problem. Earlier, before I mentioned that newtons per meter squared does not add up with atmospheres. When you look at rho v squared, rho is in kilograms per cubic meter. Velocity is in meters per second, or square meters per square second. I'm going to cancel out only one of the meters, and I'm going to change this into 1 over meters squared, kilograms, meters per second squared. And this gives you newtons per meter squared. Rho v squared and rho gh both use newtons per meter squared. The natural units coming out of those equations are newtons per meter squared. I gave you atmospheres for the beginning of the problem. So the thing that you have to do is convert that pressure from atmospheres to newtons per meter squared. Otherwise, it won't add up correctly. So this becomes 10 times 1.013 times 10 to the 5th plus 1/2 1,000 V1 squared 5 squared minus 1,000 10. I didn't give a height. 20 meters. Hopefully the math will work out right. Minus 1/2 1,000 V2 squared. V2 came out as 6.25. And you got that. And so this is the pressure in newtons per meter squared. 5 minutes. 10 times 1.013, 10 to the 5th. Plus, another reason why I love using nice densities, 1,000 divided by 2 is 500 times 25 minus 10,000 times 20 minus 500. And this is another reason why when I write a test, I got to make sure the numbers work out. This may put out a negative number, though I doubt it. Yes. So this is 8.06 times 10 to the 5th newtons per meter squared. And so that gives you the pressure in newtons per meter squared. Had I asked for atmospheres, you would take those three terms and divide by 1.013 times 10 to the 5th. And once again, as a reminder, that number, the 1.013 times 10 to the 5th, see, I've used it like 20 times today. That will be on the sheet of equations. All right, that's it. 1 o'clock tomorrow in Bishop for tutorial. See you then.